In JavaScript, all numbers are internally represented using the IEMNS 754 standard for floating point numbers. This representation can lead to unexpected behavior when performing arithmetic operations, particularly when dealing with decimal numbers. The core reason for this lies in how these numbers are stored in binary format. Decimal numbers like 0.1, 0.2, and 0.3 cannot be represented perfectly in binary with a finite number of digits. Instead, they are approximated. These approximations, while very close to the actual decimal values, introduce small errors. When you add 0.1 and 0.2 in JavaScript, the result is not exactly 0.3 due to these accumulated approximation errors. The value is extremely close to 0.3, but it differs slightly at a very fine level of precision. Therefore, when you compare 0.1 plus 0.2 to 0.3 using the equality operator, JavaScript evaluates whether the two values are exactly the same. Because of the tiny precision errors, the comparison returns false. To illustrate, consider the binary representation. A simple decimal like 0.5 can be perfectly represented in binary as 0.1. However, 0.1 in decimal translates to a repeating fraction in binary, similar to how 1/3 is a repeating decimal. The computer must truncate or round this binary representation to fit within a finite number of bits. This truncation introduces the approximation error. Now let's discuss how floating point numbers are typically stored. The IEMNS 754 standard defines formats for representing floating point numbers, including single precision and double precision formats. Double precision, which is commonly used in JavaScript, uses 64 bits to represent a number. These 64 bits are divided into three parts. Firstly, the sign bit, which indicates whether the number is positive or negative. Secondly, the exponent, which determines the magnitude of the number. Thirdly, the mantissa or significand, which represents the significant digits of the number. The exponent and mantissa work together to represent a wide range of values, from very small to very large. However, because the mantissa has a finite number of bits, not all real numbers can be represented exactly. This limitation is the root cause of the precision errors we observe. In practical terms, this means that you should be cautious when comparing floating point numbers for equality in JavaScript. Instead of directly comparing them using the equality operator, it is often better to check if the absolute difference between the two numbers is less than a small tolerance value. This tolerance value, often called epsilon, represents an acceptable margin of error. For example, you might define epsilon as 0.1 or a similar small value, depending on the required precision for your application. The comparison would then look something like this if the absolute value of 0.1 plus 0.2 minus 0.3 is less than epsilon. If it is, you can consider the two values to be effectively equal. This approach acknowledges the inherent limitations of floating point arithmetic and provides a more robust way to compare numbers. Another aspect to consider is the order of operations. The way in which you perform calculations can also affect the accumulated error. For example, adding a large number to a very small number might result in the small number being effectively lost due to the limited precision. In such cases, rearranging the order of operations or using more sophisticated numerical algorithms can help to minimize the impact of precision errors. It's also important to be aware that different programming languages and platforms might handle floating point numbers slightly differently. While the IEMNS 754 standard provides a common framework, the specific implementation details can vary. This means that code that works correctly in one environment might produce slightly different results in another. Therefore, it is always a good practice to test your code thoroughly in the target environment and to be aware of the potential for precision errors. In summary, the reason why comparing 0.1 plus 0.2 to 0.3 returns false in JavaScript is due to the way that floating point numbers are represented and handled. The IEMNS 754 standard, while providing a powerful and widely used system, introduces inherent limitations in precision. Understanding these limitations is crucial for writing accurate and reliable code that involves floating point arithmetic. By using techniques such as comparing numbers with a tolerance value and being mindful of the order of operations, you can mitigate the impact of precision errors and ensure that your code behaves as expected. Further exploration into numerical analysis and floating point arithmetic can provide a deeper understanding of these concepts. Resources like the What Every Computer Scientist Should Know About Floating Point Arithmetic article are highly recommended for those seeking a more in-depth explanation. Remember that these precision errors are not unique to JavaScript. They are a fundamental aspect of floating point arithmetic and can occur in any programming language that uses the IEM and 754 standard. Being aware of these issues and adopting appropriate strategies for dealing with them is an essential part of becoming a proficient programmer. The key takeaway is to avoid direct equality comparisons with floating point numbers. Always use a tolerance-based comparison to account for the inevitable precision errors. This will help you write more robust and reliable code that can handle the complexities of floating point arithmetic. Additionally, consider using specialized libraries for numerical computations if you require very high precision or complex calculations. These libraries often provide more advanced algorithms and techniques for minimizing errors. By understanding the underlying principles and employing appropriate strategies, you can effectively navigate the challenges of floating point arithmetic and ensure the accuracy of your calculations. Ignoring this can lead to unexpected behavior and potentially serious errors in your applications. Always remember to test your code thoroughly and to be mindful of the limitations of floating point numbers. The example of 0.1 plus 0.2 not equaling 0.3 is a classic illustration of these limitations, and it serves as a valuable reminder to be cautious when working with floating point numbers. This is a fundamental concept in computer science and a crucial aspect of writing reliable software.